Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. All right, so our next speaker is Richard May from the Pacific Northwest National Laboratory, or Pacific. Is it Pacific Northwest?
Yeah, Pacific Northwest, yep.
National Laboratory, and he'll be talking to us about collaboration in directly mediated interaction environments.
Well, thank you for inviting me here. This is my first time to WACE, but I'm already quite impressed with it. It's going to be a great couple days. This work is going to focus a lot on what I guess we'll call small group collaborations. What I want to do is kind of introduce some of the work that we've been doing. So I'll show a lot of different applications, have a lot of different video segments, and I'll pepper in between that discussions on performance evaluation. This is going to focus a lot on different technologies or different types of approaches for what I'll describe. And one of my big hang-ups is that we tend to create a lot of these things and never really evaluate their performance. So I'll talk about the simple efforts we're trying to do to start to understand how these systems work relative to solving some real problems for our clients, which are going to be scientists and information analysts for it. Then I'll kind of switch gears a little bit, as time permits, and take a look at visual analytics, which is an area we do a lot of work in for visual analysis of large numbers of documents and how to help people understand those documents. And the work we're trying to start to look at to move those into collaborative environments. Most of our work to date has been on single-user desktop environments, but we're starting to look at that now for mobile environments and for large screen work as well. Start with probably the mandatory slide about Pacific Northwest National Lab. Like Argonne, one of the DOE national labs. The group that I work with is about 400 people in computational and information sciences. The focus is on lots of things, actually. We do networking, cybersecurity, data foundations, data management, interactions, the type of work I'm going to show here, and the visual analytics groups. And that group has been growing, and we've been trying to do a larger and larger work population, or larger and larger collection of work in that area. And let me know actually when we get to the videos if they're too dark, because then we'll try adjusting the lighting. Some of the videos I have good lighting for it. I had professionals come in and do it, and some lighting I did, and that's not quite so great. Also, because it is a workshop, I will try to keep an eye out for people, and please feel free to ask questions during the talk as well. That would be encouraged in a workshop environment. The first thing I want to do is kind of set the foundation on the sort of collaborative environment we're looking at. I refer to the work that we try to do as directly mediated interaction, I think because everyone has to define some term based on what they're doing. But it goes back to Snyderman's definition of direct interaction and then builds on from what Hiroshi Ishii defined in 1994 in some of his papers. But it really focuses on the type of interaction that you do when you have a touchscreen environment. And that is rather than the mouse and keyboard where you have an interaction space here and a display space here, and we use a cursor to do the mapping between those two spaces, we want to bring the two together. We also want to look at issues of natural interaction, which is a loaded term, but one we can use and then go through and define, where people can use actions they take from the physical world, such as pointing, gesturing, grabbing objects, using objects, and having those objects have meaning in both the electronic space and the physical space. So we're talking that sort of small group interaction environment as we go through it. Designed from the get-go to be for multiple users. That's why I was really intrigued about coming and talking about our collaborative applications. So we're looking at small groups of people. The image there kind of shows our base environment that we work with. We have a desktop display that allows for it, and then the wall display as well. And I'll go into that in a little more detail. But I was going to bring that up because it's going to show up in several videos, and we'll come back to it. We're not limited to that sort of environment. As I hopefully will touch on the end, we also do a desktop where we take these ideas and move it to your desktop. We take these ideas and we actually move the system out and interact with people in a room environment as well. Or onto a wall. Shift, if most of our interactions on a table, shift it 90 degrees up onto a wall. One of the other big areas in this research has really been minimizing user encumbrance issues. To me, I started out in scientific visualization in the 80s and early 90s, and then switched over to VR applications in the mid-90s. Probably some people in this room did as well. And then one of the problems we had that with our client, scientists primarily at the time, was the cost in the sense of time and ability to get into and out of these environments, putting on the headgear, putting on the gloves, getting access to a calculator. Well, you can't get access to your calculator? We'll create a calculator for you in these virtual environments. And that works for many cases, but in our environments that just didn't work. So a big part of this work is using video tracking capabilities, things where people can walk up and use the environment without having to put any equipment on, without having to go through a calibration period, and those sorts. The other thing is, as probably this audience is well aware of, when you want to create interaction environments like this, you really need to support new interaction types. Unfortunately, we can't really take the words Office Suite and move it into an interaction environment like this and be able to use it directly. It's designed to be used for a single user with a mouse or with a keyboard. When you start to bring in different interaction environments, it doesn't work very well. So a big part of our work is trying to understand how to create those sorts of environments. So the system, for any of you who've done work in this area, this is real basic. This harks back to MIT's work with the Mediated and with Jun Rikamoto's work for the HoloWall and lots of different capabilities. The configuration is really simple. There is a projector that sits under the table. I prefer the under-table projection approach. With IR lights under the table as well, we can talk about the IR lights, but basically it's controlling the lighting environment for easy image segmentation and those sorts of capabilities. The projector and the mirrors, everything to optimize. So the table surface is a rear display screen. Take this one, reverse it around, same sort of capability on there. There is a camera over the top of the table. For our work, that's critical. What that provides for us is an interaction volume over the table surface. So it's not a touch screen. You can touch the screen, and we have some other capabilities for that. But any interaction over the table, or if you tilt it and point it at a wall, in front of the wall, or if you move the camera higher and interact in the room, any interaction in that room is tracked by the system. And that's where our software goes through and try to recognize what is happening in the environment. All the hardware is off the shelf. We're still using standard NTSC cameras for our work. We're kind of looking at going into digital cameras, but that always drives the cost up of the system and everything else. So we're still using pretty standard. Everything is standard hardware on there. In essence, what this system does is, like many others, it creates new types of input devices. They're not necessarily meant to replace the mouse and the keyboard, but at a minimum they're meant to supplement the mouse and the keyboard. So fundamentally there are two types of input devices, the hand or a pointer and an object. What the system does when a hand reaches in is detected by the camera, and we'll show videos showing different applications of this. It tracks any number of hands that reach into the camera space. So it provides to the user, just like the mouse will provide you what's the position of the mouse, what's the key button or the button presses on the mouse. It's where the hand enter the space. Where is the pointer going to? How many digits are they showing? In some cases, what is the hand pose information? All of that sort of information is fed to the user to use it in any way they want for an application. I'm sorry, fed to the user, fed to the application developer to use it in any way they wish. Another example is on the objects themselves. Any object that is placed onto the table recognizes the shape, the size, the position for any number of objects. So again, it's up to the user. If they want to only recognize small round objects, they can filter those out, or filter out everything else and just use the one object set for it. Actually, I am going to grab wire. So that's the basic configuration. We change it around on a fairly regular basis, but this is considered to be the common one that we use. So what I'd like to talk about first off then is some examples where we've used this technology in public settings, or what I will probably fall back and refer to as location-based entertainment. It's an area we looked at a lot and talked with a lot of different people about and did some playing in this area, mostly because it provided a simple environment to take some of this work. So some of the nice things about this technology for location-based entertainment, small group collaborations, is that it supports multiple users inherently. We don't have to add it and modify it if we want to support 2 or 3 or 5 or 6 users. The only problem we run into is how large of a table do we need to build and how much resolution can we get of our devices. Also, there's no worn devices. The way this works with the camera tracking is that people walk up and start to use it. They don't have to put on gloves, no painting in the fingernails, that sort of an approach. Again, just to try to get people in and out quickly. When we talk to the market sector, one of the big problems they always face is throughput. How do you get people in and out of this thing as quickly as possible so that they can get in and get the next person going? No collaboration users, and then no exposed equipment. The other big problem at different museums is anything that's exposed for a user will be broken rather quickly. And I'll show you the next example actually after this one that we did for the Seattle Art Museum, where we had to definitely avoid that, especially where children are involved. Because actually that's the first one. So one of the I wanted to show, this is in conjunction with the HIT lab here at the University of Washington, the Human Interface Technology Lab, when I was here pursuing my PhD. And we combined this technology that we have up and going along with the AR toolkit. If you're familiar with the AR toolkit, developed by Dr. Kato, I think he's at Hiroshima University now, and Mark Billinghurst, who's now at HIT Lab New Zealand and doing work. What we did was we wanted to create an expedition, or the Seattle Art Museum wanted to create an opportunity where they had a Szechuan exhibit, artifacts from Szechuan, China. But they wanted to show these artifacts in an environment that wasn't all cleaned up and behind glass. They wanted especially the kids to understand where all these artifacts came from. They came out of a hole out of the ground. They were dirty. They were busted. They were damaged. Why were they damaged? So there's all these questions. It turns out this particular dig resulted in redefining how they think culture developed in China. So it was very critical to understand this whole process that they went through. So we created the virtual dig, which was an opportunity for them to come in and work with it. It was essentially a 10-minute little amusement park thing. Groups of people would come around. There were 3 tables. You can see them there, just like I showed you, with a table and a wall behind. And they would come in. There would be a narrator that would come up onto the screen on the wall, and it would talk about them, tell them they're at a dig site, and walk them through many processes. I'll show you the first one that would come up, which is they would be presented on the table with a field of grass. That is going to show? Okay, so let me know if you can see this. Sorry for the lighting. It was taking real people using the system, so it was kind of dark at the time. But you can see we have 1, 2, 3, 4, 5, 6 so people all reaching in, all interacting with the system at the same time. It tracks all the people. They're brushing away the grass, brushing down through the dirt, until eventually they expose the artifacts. Now, like anything, we had to do this. If they didn't clear everything in time, we would stop it and automatically clear everything off so we could keep everyone to a timetable. But we have a whole bunch of people all working together at the same time in the environment, and they're being tracked as a series of pointers. So the application is designed to recognize as many people as you have reaching into the space at the same time, which is nice. We don't have to adjust it for 2 people or 6 people as we go through. The other things in this particular environment was the ability for, there's a whole series of steps they would go through. Some of it would be digging down a little further past some tusks down to some other artifacts. They would try to do a hot and cold game where everyone would reach in and they had to work as a group to try to recognize. So underneath their finger would appear a blue region, cold if they're a long ways away from the artifact. What they were looking for was, one of the prized possessions out of these digs was an 8-foot-tall bronze statue, but it was broken into many pieces. So they had to go in as a group and all converge on the 3 pieces that represented this statue. And so as soon as enough people all got through it, their finger would turn from blue to lighter red to dark red when they were hot over the topic. As soon as enough people all converged to it, it would stop and it would bring the piece together and then start to show the full interaction. And so it was filled full of steps like that. Another example that we constantly use on all of our demos and has been at several conferences, SIGGRAPH, and ACM1, if anyone's involved in ACM1. It's what we call virtual hockey. It's kind of when you build alternate technologies today for interaction, you have to build a hockey game. It's kind of like the hello world of interaction technologies. This is a 2-person game. So again, like the system will recognize as many people as want to interact with the game, but in this case it's going to only look 2. It's up to the application developer to figure out how they want to figure out which 2 hands they want to look at if more reach in. And I'm going to ignore my phone. There is also the hockey aspect where there's a puck and a ball. The way that it works is you reach your hand in, and underneath your hand appears the paddle, and the ball is also virtual on there. For the heck of it, we also threw in some other aspects. There's a pinball capability where you can put defenders. This brings in the objects, which we haven't seen before. You can place a small round object, which is simply a piece of wood. There's nothing technologically advanced about it. You place it on the table, the system recognizes, and it serves as a pinball bumper, so the ball will bounce off of it. So let me kind of start the video, and you can kind of see all this happening. This is also, I think this is my second dark one, so we'll see if it shows up. Can you see that, or do I need to adjust the lights? Okay. Hopefully it's coming out well enough. So you got 2 people interacting. So I asked you to look at a couple things as we go through this, because it leads into the next part of it, which is first the objects. There, I'm placing one object on the table, and the ball will bounce off it and recognize it. We incorporated simple physics into this example. If you were actually playing it, there'd be a lot of doings and whistles and bells going off every time the ball bounces off of something. It makes a noise, and we added all those sorts of capabilities to it. But also, I think we're about, as we zoom in here, the other thing to notice is underneath the finger is the paddle. That's the interaction point. Notice how it lags behind the finger just a little bit. This has become one of our big research questions is what is that? Or was one of our big questions is how much lag is that and how does it affect performance? You can kind of see. You also see the speed of the system. This is the other reason we tend to show this one, but how fast an interaction with a standard NTSC camera can be. Like any good sporting event, whenever there's a goal made, we stop and we bring up an ad. In this case, it happens to be an ad from some of our research, and we use this quite often to hook in kids. We'll bring them in with a game, have them play, and then every time a goal is made, we'll bring up an ad or a photo of some of our research and then talk to them about the science behind the research and everything, and just different areas. But so one of the key issues there was looking at the lag. Many times, we don't understand how much lag are in these systems and how much that can impact performance. So I was presenting somewhere and ran into a wonderful gentleman who introduced me to a technical paper at UNC and introduced a technique they were using to detect lag in magnetic trackers. Total system lag, and that is from the time that an action is performed by the user to the time that the system can respond to that action. The process is really simple. You have a photodiode and your physical interaction device, represented here by the armature. What happens is you simply calibrate the system, so when the arm reaches a certain point on the screen, the photodiode is activated and it sends a signal off to an AB timer switch. At the same time that your stylus, in this case, or whatever your physical action is, passes this point, the application says, light up another corner on the screen, which is represented by the photodiode on the top there. I have a laser pointer. Oh well. It's a photodiode up at the point, and a light appears there which sets off that photodiode. And what we do is simply measure the time difference between the physical action that occurred and the time that it took a light to appear on the table. So this takes the whole system process, the video capturing process, the video processing steps, also any lag that is introduced. In this case, we're using a standard projector, which introduces a 1-frame delay for anything before it pumps it out. So it takes a look at that total end-to-end lag process. For our result, take a look at the normal, 30 frames per second. We ran 3 different trials on it. Again, they're pretty boring trials. It was all spring-loaded, so we could keep consistency on it. We came up with 71 milliseconds of lag with 11 millisecond standard deviation consistently across. Okay, not an exciting number, but a very interesting number for us, because that's not an insignificant amount of lag when you're just talking the input device alone. That definitely rivals those of immersive technology devices, such as magnetic trackers and those capabilities. I think I'm going to skip the lower part. There is some interesting, we also ran some interesting studies to look at what happens if the system slows down to 10 frames per second. Again, 30 is our maximum because we're using an NTSC camera. But what if it slows down to 10 frames per second? There are lots of reasons that can happen. It could be on the input device itself, that is our ability to image process and everything else. Or it could be due to the application itself being the time hog. It's got a graphics it's got to generate, or it's got computations it's generating on its own. Or the bottom one, the skip frames, is the trivial case. The point that came out of here that was critical to me is that your image processing, or that is your input device, has to be as fast as possible and not be the bottleneck. Because when you constrain the data that far down the pipeline, that's when you introduce the most lag into your system, which is going to make it not usable. Okay, I want to switch into a couple other examples. Oh, I'm sorry, yes?
So you said that 70 milliseconds was incredibly interesting to you.
Well, it was interesting because, yeah, go ahead.
But what's kind of the usable range? So you suggest that 200 milliseconds is...
Actually, let me address that question, please. Partially, depending on your task, it actually isn't a problem to some limited degree. And I'll show a study actually later on. We'll take a look at that, at the issue of lag, and then talk about how far we want to go. I think it's like anything is it can become a problem, especially with moving targets. And we haven't really progressed far enough to study all that. But you saw in the hockey game, the 71, and that game's running roughly at 30 frames a second. The lag of the system wasn't causing a problem in most cases. It required an acclimation period. People had to kind of learn that lag factor for it. But we did an informal study where we had a group of people in who, I did this down at SIGGRAPH. At the end of the day, at SIGGRAPH every day, this is a few years back, we had the crew would come in who did all the facility setup. And they would come in and play the game. We'd have a hockey tournament after it was over. And I did an informal study where I'd ramp up the speed of the puck and just keep ramping it up and ramping it up. And it was very obvious that at a certain point, even though your hand could get there in time to stop it, the paddle itself couldn't get there in time that represented your hand. So there is, in fact, a limit to it. What it is, I don't know. But I'll also address that a little later on with one of the studies. Carney signs is another little application was put together, a little bit on the history just because the Carney signs name doesn't make any sense. At one of my demos with the hockey game, a friend of mine who happens to name Chris Carney is his last name, said it would be great if we could do gesture recognition or pose recognition as part of the system, and it'll have a little game associated with it. So this game was named after him because he was the one that gave me the impetus to actually incorporate pose recognition into the system. So what it does is basically show you a silhouette of a gesture, and then built into the system, it recognizes 8 different poses. Actually, it's using a neural net. You can train a neural net with some similar parameters. So we have a little API that allows you to insert your own neural net to recognize whatever gestures or poses you're interested in to work with it. So let's just show another little example. Again, so this is a 3-person capability, or a 3-person game. You start it off by just posing in the middle, and then 3 people reach in, and you try to match that gesture as quickly as you can. It can recognize keep gesture, it's a pose, in a 30th of a second, 1 frame. We impose a 10th of a second delay to it, so it really analyzes 3 frames to make sure you're trying to match that pose rather than just waving your hand around real quick. It's a lesson we learned from having a bunch of children come in and play the game. Sort of thing. A very simple little interaction environment, but it does show, the idea to start to use higher order interactions as part of the system, and the fact that you can incorporate simple, although fairly robust, pose recognition into the system, as well as all the other capability for multiple hands, and still run in real time. I want to show a little video here, another couple little games again, just to show the collaborative environment. Now these ones, what's interesting is they're both the same. This one is just a memory game. The idea is simply to point to and find the matching images, and once a person finds them, you can play it. It's by design a 2-person game, so 2 people trade off on finding the images for it. We run this on a desktop system. We also run this on a plasma display with a SmartTech touchscreen in front of it, and it works rather well in all the different environments for it. Again, keep in mind, in this case, we're not using a touchscreen. It's all done by the video tracking. This one is Whack-A-Mole, but probably can't call it that because I'm sure that name is copyrighted. So it's whatever we want to call it. But it's a very simple interaction. It could be a 1-person. In this case, we just kind of divided the screen in half for it. And the idea is to select those as quickly as you can. The speed at which they, or the time in which they stay in the hold decreases, and the game ends when you fail to select 5 different moles fast enough. And then you get a little message, I think pops up here in a second, that says, game's over, you failed. But notice, that task, it's a very simple task, one we use all the time in computer interactions, right? Select a menu item, select an object on the screen, reach out and select a stationary task. This led us to a series of studies. I don't know how much experience I have with Fitts model, which is a very simple model and relationship for the difficulty of selecting a target or acquisition of a stable target is a relationship between the distance between the 2 targets, which is the A amplitude in the cute little equation there, and the size of that target, or W width in this case. It started, Fitts developed it in 1954, I think. It really initially developed for physical interactions. He used it for touching of devices, moving of items over cones and things like that. But since the 1980s, it's been heavily used for understanding performance characteristics of input devices as well. So we adapted it and wanted to run these studies to try to understand the capability of our environment, which we're using as an example of directly mediated interaction, but not the only example for it. We wanted to understand, first of all, so these people are reaching out and touching these objects. Does it make sense to do that in this environment? Or is it easier to do with a mouse? Who we just say, unless you find some compelling reason to do this in an environment where you need to have hands-free, untethered sort of capabilities, and a mouse and keyboard is great, shouldn't we just use a mouse and keyboard? We also want to answer the question of lag. There is lag in the system, but yet we were playing with 71 milliseconds of lag. They were playing that hockey game rather quickly. If you look at the literature on lag studies for mouse-based systems, 71 milliseconds of lag should have really impacted performance in that hockey game. So the question is, why didn't it impact performance? Fitts is it's a tapping task. Again, just for clarification, typically it's a left-right. Typically, you're going left and right, acquiring targets as quickly and as accurately as possible. There's a trade-off between accuracy and speed. That's a careful balance when you run these studies. In our case, and what has been done mostly for computer interaction technologies, is you simply do as a discrete task, one direction only. That is, you're trying to go from a start position to select a menu item. We don't typically in computer interaction go back and forth very quickly. So for most part, that's been pretty avoided. We also had everyone hold a stylus. Again, you don't have to use it with a bare hand. You can have a handheld stylus, and the system will track it just as well. And I used a stylus for all these studies because it provided a consistent tip shape. That way I didn't have to worry about any probable error coming in from people using different sized fingers. So the task was really boring. In these studies you probably can't do for over an hour, and you have to have plenty of breaks, because literally the person standing here, select target, select next target, over and over and over. Not what you want to be an undergrad student and get involved in. So the first study was looking at a mouse. So we had them perform this task on the desktop and on the HiSpace system, the system you've seen in the videos so far. And quite surprisingly, for us, for the most part, so if you're not familiar with this, apologies to the cameraman as I move over. The way that a fit study goes, you have the index of difficulty. So basically, this side are the simple studies, large objects close together. As you move further out the scale, you get very small objects very far apart, becoming much more difficult to select. And then meantime is just the time in milliseconds to acquire a target. What you see there is that with the mouse system, which is the line on top, it took more time and it has a slightly steeper slope to it, meaning that the more difficult the task becomes, it takes relatively more time to select the target with the mouse than it does with the HSE or HiSpace environment, which is the one underneath it. And you can see the raw numbers down over there where it actually looks at the time in milliseconds and the error rates for it. That was quite a surprise, especially taking into account that everyone who was in this study were expert mouse users. They've been using them every day of their life for I don't know how many years. And all of this was this study was actually done at Pacific Northwest National Lab, so they'd all been using it for quite a few years. And with a few exceptions of the 14 or 15 people in the study, I forget, I don't know if I said on there, only one of them had really used the HiSpace to an extent. Many of them had never used it before, and we had to give them a little 10-minute trainer on just so they could get used to it. And yet we still got these sorts of results. The interesting point, though, when we look at error rates, is we really didn't see a difference in error rates. But I think that's misleading, partially because a Fitts law study is as quickly as possible, or as accurately and as quickly as possible. If we remove the quickly as possible constraint and just focus on accuracy, the mouse would probably be better because it has pixel level accuracy, where the HiSpace or our current system doesn't, because the camera resolution isn't sufficient. And if you kind of look down here, you can see a definite trend. This is the size of the target in pixels. So there are some misleading aspects here. We're doing a little bit of apples and orange comparison because we have this large table with people performing a tapping task, and we got, in our case, we use a standard 20-inch monitor, and people using a sliding task. So there are some differences, and we do have to be careful on how to equate those. But if you just look at the raw size of the target in pixels, which is a simple way to look at it, I won't go into the other details on it, what you can start to see is as the target gets small, the error rate on the HiSpace suddenly starts to jump really huge. You pass this threshold where it just becomes nearly impossible to acquire the target. Our system is not good enough. With the mouse, it's a pretty consistent growth pattern because it takes more time, but you can get pixel level accuracy. So there are some long-term issues there. Also, kind of as an addition to this, the whack-a-mole game, the one where they're selecting the target. We run that, like say, on a 50-inch plasma screen with a SmartTech touch panel in front of it. And there, they can actually perform it faster there than they can on the HiSpace. So I think there's definitely some mixes in between on the capabilities. The feedback study, this one was interesting because the question came up after doing the first study where we compared the mouse on what was the impact of having a cursor. Did you need a cursor representation in directly mediated interactions? That is, or are you using your finger as your cursor? And in fact, a cursor is not even required in order to perform the task. So we did another Fitts law study that had them doing the same task, but there are different feedback mechanisms this time. In one case, they had a cursor, simple crosshair cursor to represent their position. So when they held their finger over, there's a crosshair underneath their finger, and that represented the region of interest. So when you acquired a target, the cursor would show you if you're inside that target or not. There was another case, it was an audio response that would simply say that after you acquired the target, there was no physical representation, so no cursor. But after you acquired the target, you'd get one sound that says it was a success and another sound, that said you had failed. So you kind of have that sort of feedback to tell you whether you had successfully acquired the target. There was the combination of the two, where we combined them both together, provide both forms of feedback. And then there was the no feedback condition, which basically said, you're not going to get any feedback at all. You're going to run through this study. You'll never know through the entire time how many you made successes on or not. Still try to be careful and balance accuracy versus speed. Basically found very little difference in any of the cases. The feedback mechanism provided very little input as a whole. Now again, these are stationary targets. target, so this is very limited in its scope of meaning. Except in the case where you had very difficult targets to acquire, at which point the cursor actually did definitely improve accuracy and improved accuracy at the expense of taking a little more time to perform the task. So what we think is happening is that when you have small targets and people actually have to pay very close attention, they'll slow down, look, and the cursor provides visual feedback on whether they're acquiring the target. Kind of what you'd expect. This is then the lag study that was mentioned, which basically looks at the issue of how did lag impact individuals' ability to acquire targets. Again, we're talking a Fitts law study here. Bottom line is, for acquiring stationary targets out to about 400 milliseconds, lag had no ability to acquire an initial target. The end result, they're using their finger to acquire the target. So if we provided a feedback of a cursor, and that cursor would go you, but if it was lagged behind by half a second, they would still acquire the targets just as effectively. So for single access of individual targets, it's very interesting is that they actually use their finger, and lag doesn't tend to play a huge role in the performance. We need to move that and do another study looking at issues of moving targets as well. Oops, let's go back on to that. So these sorts of studies, while primitive, have really helped us define where are the areas we need to improve the technology and how do we need to go through it. And I think these are the sorts of studies that before we can start to say everyone should go out and use touch screens and pointing devices and different technologies, we need to understand where the strengths and weaknesses of these technologies lie. And one of our problems is we really need to improve our resolution. Before I kind of move on to more complex things, just another quick video of an application. This is a simple paint program. Person reading further is Bob, one of the other researchers there, and he's doing the drawing. And I'm more on the side using a widget we've created that changes the width of the paint line by creating a dial device. I think the next little segment shows that further. But the idea of two people working together. In this case, Bob is actually multitasking. He has to not only draw the line, but he also is changing the color of the line as he goes through. So again, we can track as many people as you want, as many pointers as you want. It's just up to the individuals. So you can start to build a collaborative paint package and allow people to do things. We should have probably brought in a third person, had them dynamically change the color through the sliders. But Bob did an okay job. The next application is a project now. Now what we're really trying to do is ramp it up. We've got some base studies. We've got some rather simple applications. We really want to look now at issues of how can we start to analyze these systems and determine if they're useful for doing real work. Painting, games, those are nice, they're neat, they make great demos, but they're not going to help a scientist understand their data. They're not going to help a biologist understand the workings of the Shionella or any sort of organism that they're trying to understand. So we have a project, a 3-year effort, we're in the 2nd year of it now, working with Annie Van Dam's group at Brown University and Mel Slater over at the University College of London to take a look at biologists' data from confocal microscopes and develop environments at Brown at the cave system, in our high space, at our workplace at Battelle, and on the desktop as well. And what we're trying to do is develop these systems so they have the same functionality optimized for each of these 3 environments, and then look at how can you then take and measure performance. So we're starting to run a series of user studies now to look at performance issues of scientists, or in the case of Brown, some grad students, really looking at confocal microscope data and trying to solve real problems and taking a look at the different approaches used for it. Now, to do that, one of the things we ran into is we really need the capability to create very complex applications. Windows talking to Windows, all kinds of multiple level stuff. So far you've seen our examples where we keep it pretty simple. Most of them actually have been developed with our architecture. What we do is we create the environment where we have the base libraries are recognizing fundamental tasks of pointer and pose and object and shape and speech and all those sorts of things. But on top of that, again, still within the library, we create higher order interactions. Gestures. Now, we don't apply meaning to these. These are at the input level device. But we apply and recognize certain type of gestures. So you might want to perform one gesture as a sweeping motion. So some real common ones we've picked is if you make a gesture and do a sweeping motion, that means delete. Or if you shake something really fast, that could mean delete. And those sorts of capabilities. Now, we don't apply the delete meaning to it. We just say we recognize this predefined list of gestures. If you wish to use that in your application. In several examples, we've incorporated speech into it as well, and have just recently started to allow user-defined sorts of interactions. These are fed over to the application. The application, and what we've done in Java, is then taken extensions of most common components, so the windows and panes and buttons and dials, and we've made them high-space aware. And we've put a manager on top of it that allows the passing of all these events between the objects to follow a logical pattern for multiple users as well, which is one of the other problems. Now, all the objects can be high-space aware. So when you saw on the table there that Bob was interacting and changing the color, we can have the high-space system recognize that and forward it on. Other examples is we can have two hand gesture actions now. One action in this window, one action in another window, and have them relate. One of the things we do is linking windows. If you have a hand in each window, the two windows will link, and then their actions now are performed in unison sort of capabilities. But this architecture was really critical for us to be able to dump out these applications very quickly. We're actually quite happy with the way that it has turned out for us. So the actual interface to what we call BioApp for bioapplication allows users to select data sets, bring them up, manipulate them in fairly common ways at this point: rotate, scale, change the alpha value, zoom in, place markers, some simple annotation capabilities. And we do this through a series of windows. So we'll just show a video here showing some of the applications. Now we do this in the two-screen system. So on the table is we're looking at the interaction aspects, and up on the wall is where we're going to be seeing the data sets moving around. I think in the second half of this clip is where we show the data manipulating. You can open a window, so you can open this little side panel, select windows. You can also open those objects. We have a built-in shape library. So again, the underlying library just says, I recognize these shapes. The application says, if you put this shape on the table, I'm going to open that window for you. We also use speech. You can verbally define which window you want to have open and have it open on the screen as well. You dynamically move the windows around. You can support two people or multiple people working together, understanding and looking at the data. That sort of capability. Brown has an equivalent with their cave environment. We're slowly expanding the functionality and then slowly running user studies and asking them to perform tasks, just finding particular items. So in some of these data sets, they've been trying to understand it and they're looking for particular artifacts. So we have the lead scientist who's been looking for these artifacts tell us about it. Then we have other scientists who don't know where it is, but we can describe what they're looking for and have them try to perform this task in all three environments and try to measure performance capabilities. Okay, so that's really the end of the talk that deals with the high space and the directly mediated interaction. What I wanted to briefly kind of go through was present some of the stuff dealing with information visualization. Get a little bit of a background on what information visualization is, and then why we're moving that to mobile devices and kind of show what we're doing. We're really excited that as a collaboration environment for teams. Typically, if you think of the analyst is someone sitting in an office staring at their computer screen dealing with lots of information. What we want to do is allow this to move out to the field investigators now, where the field investigators can have access to that same information, provide real-time feeds back and forth. But they're not just an input. We want to provide analytical capabilities for the teams in the field. So information visualization, or visual analytics, or whatever term you want to define for it, is really the aspect of this talk is looking at very large numbers of documents, tens of thousands, hundreds of thousands of documents, and trying to come up with visualization and techniques to understand those documents, especially when the analyst is someone who's looking at the documents and doesn't even know what they're looking for, but they know they're looking for a trend, and they know it has something to do with some topic they've been told to look at. So what you're looking at here primarily is what we call the galaxy visualization, off one of the visualizations we've created, or suite of visualizations. Each spot of light on there represents a document. They've been clustered by multidimensional scaling and using k-means and other types of approaches to deal with it. They're all clustered based on a syntactic level, so primarily it's looking at frequency, co-occurrence of different terms sort of approach. I didn't actually do that work, so I can't actually talk in any detail on the on the underlying mathematics for it. But it has worked out rather well. The whole idea of visual analytics is really not so much data, not even so much interaction and not visualization. It's really trying to get insights. It's trying to get to the end result from raw data, that is documents, to getting insights to the analyst to be able to answer questions faster and more easily. So we tend to refer to, the common term as the discourse. We're really looking at that discourse that occurs between the analyst and their environment to get to an answer. Now that discourse can occur on a desktop system, it can occur on a large wall for groups, and it can occur out in the mobile environments as well. Why mobile devices? Well, at the high level, the mobile devices represent some interesting environments. I think these numbers I took from EU presentations, actually, a couple months ago. So, it's becoming ubiquitous. Huge number of mobile devices appearing in the world. Cell phones are a good example. And they're also the data collectors now, whether you know it or not. Cell phone or cell service provider in the world is collecting constantly the strength of your cell signal. And it's information they're gathering every day for helping to monitor their environment. That's only going to get more. The next generation of cell phones, the smartphones, will start to have RF readers. One of the real big examples they're looking at is just at time, or that in the EU they were talking about was just in time pricing for produce, as an example. Those little stickers that you find on the bag of apples will at some point probably have an RF tag in it. And you can take your cell phone, go up there with your RF reader, it will tell you when was that package of fruit shipped, how long was it shipped, what was the average temperature during the shipping, how long has it been in the store, and what's the current price they're charging for that. Because what they want to do is charge more for fresh items and for less fresh items so they can get them off of their shelves. Now, at the point where a package of fruit in the store is telling you all this information is when we really start to reach information overload now. And fruit can tell us that much, we'll get information from all kinds of sources. So this really represents an issue that we have to understand and be able to deal with huge numbers and huge amounts of information coming from all kinds of directions. The other reason that mobile devices are important for our work, what I showed previously are what I would call public spaces, a little bit like the discussion a little bit earlier today. These are environments where it's a large screen, everyone sees what you're doing. That's not always the way people want to work, especially we've discovered with our scientists. A lot of times they want to take a piece of information, run off and work on it, so they make a mistake, no one sees they've made a mistake until they get it the way they want it, and then they push it out for public consumption. So this to us is providing a means to improve our ability to develop private workspaces on small devices and the communications between those private spaces and public spaces, and develop those small group environments in that way. Most of this is pretty straightforward. We're looking at different applications and where visual analytics is important. We're trying, again, not to make the information just simply a feed to the user like you would feed them a video, but rather feed them information they can then work on themselves and analyze and deal with and send results back to the home base. So we're trying to look at those capabilities. One of the big questions for us was, what role does visual analytics really play? This is, for the most part, an unexplored area. How much interaction is required? There's a school of thought, for the, probably aware of this in the mobile environment, that in fact we shouldn't have any visualization on mobile devices. They just distract from you. It's fine. You're meant to be staring at that screen. In the physical world, you're meant to be watching where you're driving, watching where you're walking, taking in the sunset. And the device would probably be down here with audio signals, and you could respond by diddling around on the screen or pressing keys or that sort of thing, but not even have a visual component. For us, that's not a solution. We haven't found a way around providing complex visual information to people. So we're still trying to keep that. But the role of it is very important for us to understand. And as would be expected, we know you can't just take all these visualization techniques that we've developed for desktop environments and shove them onto a PDA. For all the reasons we discussed, both the display, input capabilities, but the environment and the focus of attention. Sometimes people are going to be riding in a bumpy car, moving in an emergency situation, and they're not going to be able to spend much time to do delicate interaction or to stare at it for very long because they're going to have to look for other things. At other times, they might be sitting in a cafe with their laptop with a latte and have lots of time and detailed look at what they want to do. We have to support this range of capabilities. So that's what we're really looking at. How do we scale both at the visual, the interaction, and at the data level between all these different possible devices and environments that the person can exist in? So this is a big part of our research that we're looking at. We're really looking at 5 different types of visualization and how we map, how the groups can look at them at the same time and work with them. The two I'll give a really quick example on is cluster visualization, which I showed when you saw all the documents there in the Galaxy view, and a little bit on maps with one of our partners on these projects. So the cluster visualization is problematic on small devices. You went to supercomputing last year and tried out InfoStar, and if you did, was an example where we took our Galaxy visualization and moved it onto the laptop. And for InfoStar, what it does is InfoStar is an effort at supercomputing to provide real-time information to the conference attendees. So they can do searches. We updated the conference information, including exhibitor information, about every 10 minutes. provide them this galaxy view as well, where they could see where everything clustered and how the documents work together. And so you'd have hopefully everything clustered around one area if it dealt with similar topics such as high-speed networking or grid computing and that sort of thing. The clustering worked fine. The problem was you couldn't really use it in the mobile environment unless you were really sitting down and really taking care. So this is actually a preview of what we'll have at Supercomputing 2000. I guess it's 2004 last year. Sorry, I apologize if I misstated. At 2005 this year. Well, now what we've done is we've said, okay, we're applying a different set of techniques, and we're going to provide a user-definable number of clusters. So in this view, what we're doing is we're allowing them to define how many clusters. The numbers over there on the far side is basically the number of clusters you want to break your data set into. Depending on how many clusters you select, it will then go through the documents contained in each of those clusters and find the key terms associated with that. So what's the meaning of this cluster, or at least what's a representative meaning of this cluster? You can click on a cluster and drill down into it. So for example, if you pick the cluster that says Middle East, Iraq, and conflict with 104 documents in it, you click on that, it would take those 104 documents, break them into a representative set of clusters. The default would be the same number you had above, but you can find to go less or more depending on both their device and their environment, and find the information. Eventually you drill down far enough, you can then take a look at the actual documents themselves, sort of thing. We're working with Natural Interaction Systems, which is a small company based around the Portland area. I'm not exactly certain where they are. And they do a lot of work with mobile devices for multimodal. They do a lot of work on speech and pen input capabilities, and have recently worked with Smart Paper. We'll kind of show a video of Smart Paper. This first video, there we go, it starts up, just kind of shows some of the work they do in multimodal, where we're looking to take and also move this down to mobile devices. So what's happening is someone is marking on a smart board. It's being fed over to a. They're augmenting, we don't have audio, but they're augmenting what the information is with speech. So you can assign meaning to it through speech and communicate back and forth between the two groups. Primarily this application is meant for the military. So they're doing military, I think the next video is too. They're doing military sorts of things where they're marking troop positions and movements. Their portable environment that they're working on is looking at Smart Paper. Smart Paper, for those who don't know, it's basically a paper that has very small print on it. So slightly gray. You work on it with a pen that has an optical reader in it that can read the marks on the paper. So if you've pre-coded this paper for, let's say, a map, anywhere you write on that map, the system uses Bluetooth to connect back to a computer and automatically feeds those back to a computer for augmenting. The nice part about this is you can write anything. So you can think of it as a search criteria. If you're searching through hundreds of thousands of documents, and it's dealing with a natural disaster, you can circle an area, put a name or put a date, and then you define your search query to go into the system. That region is fed in. If you've got the geospatial name, the dates are all fed in, and the search. And then you could go to, let's say, the cluster view I showed you earlier. So we're looking at how you can take this very physical interaction and apply it as both an indexing medium and a way to control the sorts of searches and interactions you do. It's also very nice. You can fold it up and put it in your back pocket. You can literally rip this stuff and hold it back together and draw on it. It still works. It's really pretty cool stuff. You can find, if you're interested in Smart Paper, you can find it on the web. There are several companies selling different versions of it. Actually, like I said and mentioned at the beginning of the talk, we're looking at different ways to do this as well. The work on the table environment is our standard one because it's easy and it's something we don't have to reconfigure very often. But we've done research where we've moved out to a room, so we track people working around in the room, as indicated over there on the far side. Walls, and then also big efforts is take and shrink it down to your desktop. So now on your desk, you could have your mouse, your keyboard, but you could also have your interaction space where you can put an object out there. You could lay an image, you could manipulate it around and do those sorts of activities with it. And that's a summary of a lot of the work that we're doing in this area. We're hoping to go. So any questions on that? Of course, I'm available after and everything as well. Okay, thank you very much.
Just one quick question.
Oh, yes, I'm sorry.
Are you looking at distributed collaboration in your
We haven't found, I mean, yes, I'm very interested in distributed collaboration. We've done a little work with having multiple tables work together. In fact, the architecture that I presented, one of the aspects of it I didn't talk about, is it supports an IP manager as well that will link together all kinds of different tables, or you could make it a mobile device or a traditional desktop. Honestly, we're looking for collaborators in those areas. We don't currently have a need to do that work, and Battelle, like most national labs, we do application-driven research. So until we can find an application and someone who's interested in that, and we could co-op and work together to write a proposal to someone, we just haven't had a chance to pursue that direction.
Is the high-space software out there available for folks, or is it kind of closed?
It's not. If I had my way, it would be out there, but unfortunately, I'm just a researcher, so they don't let me have my way very often on those sorts of things. But it is available. We've got collaborators at OGI, Penn State, University of Washington. I can easily get it to you. It's just a matter of coming up with a simple agreement to do research and stuff with it. And we're always looking for people. I am hoping at some point to put it out there. If you know Mark Billinghurst in the AR Toolkit, Dr. Cotto, who is the creator of the AR Toolkit, as far as I'm concerned, he did the best thing in the world. He went out and made it public domain, so you can use the AR Toolkit, which is a design for camera recognition system as well. So we're looking to do that, but I wouldn't count on that in the near time. But if you're interested, be happy to talk about possible collaborations. Okay, thank you very much.